Hi, I'm Don Dooley, President of Spectrum Detector. We're going to be showing you a brief demonstration video of our new Mach 5 100 kilohertz digital joule meter. Let's head to the lab and we'll get that started. We're here in the lab, but before we get started, let's take a look at the Mach 5 hardware we'll be using as part of the demo. What I have in my hand here is one of our fast silicon joule meter probes. It has a range of 200 nanojoules to 200 microjoules, and it's a detector. It made it to an integrating circuit that includes an EEPROM that carries the calibration data and wavelength correction data. It also includes a thermistor in the package to monitor the sensor's temperature for temperature correction if necessary. It's made it to a small integrating sphere. And then there's the Mach 5 digital instrument. This is a fast microprocessor, 12-bit A to D, full-speed USB, 2.0 USB, and let's look at the back of the instrument first. There's the input for the probe over here. It's a LEMO connector. There's a BNC connector for analog output, 0 to 3 volts, and there's a TTL compatible trigger input. On the front of the instrument you have a power switch, you have the USB connector, the power connection itself, a trigger lamp, overload, and armed lamp, and then a couple diagnostic lamps here if it's out of range or over temp. Let's take a look at the optical setup before we start the Mach 5 demonstration. We're using a 100 kilohertz YELF laser. This is the JDS Uniphase power supply controller for the laser. This is the laser head. This is an optics holder and an ND filter to attenuate the laser beam. This is one of our fast joule meter probes connected to the Mach 5, which is in turn connected over the USB to our laptop that's running a Mach 5 LabVIEW application software, and the analog output from Mach 5 is connected to our digital oscilloscope over here, so we can take a look at the actual pulse-to-pulse oscilloscope screen here, where you can see sampling of the pulses. We're set up here at 2.5 microseconds per division. We're looking at 4 divisions between pulses. That's 10 microseconds, which is exactly what you'd expect for a 100 kilohertz laser. Let's go ahead and get the demonstration started. We have the YELF laser on, running at 100 kilohertz. You can see the beam on the infrared card. We're in the live mode of the instrument, where we're displaying the pulse energy, getting sampled at 10 hertz. You can see the effects of dropping an ND filter in, which we're going to use in this experiment when we take the data live. Let's go ahead and go back to the main menu and set the instrument up to take a data set. We're going to go ahead and arm the instrument to take real data. I've set a batch size of 300,000 pulses. That's 3 seconds of data, and that'll give me time to drop the filter through the beam. So let's go ahead and arm the instrument. Taking data now. Drop the filter. Okay, we've got the data. Let's go ahead and look at this data in the strip chart mode. We'll go to the tabs up the top here and select data strip chart. Here's 300,000 pulses. You can see where the filter and when the filter was dropped through the beam. Lower energy, and in some cases no trigger. Let's use the convenient LabVIEW zoom feature here and zoom in on this area of the data set. Now here you can see the effects of the filter going through, energy transmitted through the transmissive part of the ND filter, and then the frame again. This is the data you wouldn't be able to collect if you weren't running at 100,000 pulses per second. Extremely useful diagnostic for high rep rate laser users and developers. Let's take a look at just a couple more screens. Statistics mode. This allows you to look at the pulse energy, min-max, standard deviation, spread, variation, lots of other calculations at your disposal. In addition, in this mode you're able to look at the missing pulses. There's 2 categories of missing pulses. Pulses that fall below the trigger. Well, these are the pulses that were caused by missing trigger, and then also pulses below an energy threshold that we set at 60 nanojoules. Extremely useful, again, when you're developing a process, you need to know the effect of missing pulses. Let's look at a couple of the other screens that are available. There's a data histogram where we've plotted the data in a bar chart basically and fit a Gaussian curve to that. Full statistics displayed at the bottom. There's also an extremely useful diagnostic mode. It's a FFT mode, so you got a fast Fourier transform display here where you're able to look for periodic disturbances in the data set. Could be very useful for diagnosing a power supply problem. And then another mode that is also very useful is the life test mode, where you're able to go in and set up a life test for hours, for days. You actually set the start time and date, stop time and date. You set the batch size. You can set the frequency or the total number of tests you take. It records that raw data or statistics, if that's all you're interested in, puts them in the file sequentially, labels them, and when you come back hours later you have a complete history of the laser performance over time. I think this is something that your manufacturing engineers will find very useful. That concludes our demonstration of Mach 5. I hope you found it interesting and useful. If you have specific application for Mach 5, give us a call or visit our website where you can download the datasheet, a manual, and an application note on Mach 5. Thanks for joining us today.